So now we've got our neuron, right? Our brain cell here at rest, which means that the inside of the neuron is more electrically negative by about minus 65 to minus 70 millivolts versus the extracellular side. And that's, of course, maintained by the impermeability of the membrane. Remember, it's a phospholipid bilayer, which does not let charged particles easily pass back and forth. And there are only a few of these non-gated sodium channels that are embedded in the membrane that allow for, at rest, sodium to pass through. These are actually referred to as leakage channels because there were so few of them. They just let sodium sort of leak in, really enough sodium to leak in to run the sodium-potassium pump, remember, which is really also doing quite a bit to contribute to that distribution of charges, that unequal distribution of charges. More sodium on the outside, more potassium on the inside, that is characteristic of the resting potential. This sodium-potassium pump is really a transporter, right? Because it's utilizing ATP, it requires energy to force the sodium out against its concentration gradient. So it's established in high concentration and maintained in high concentration extracellularly. And also it's forcing it out against a more positive external environment. Sodium's a positively charged ion. So remember, like charges repel. So you really need that ATP to break that phosphate bond, right? In this, chemical, in order to convert it into the kinetic energy required to force, that sodium out. And you're also bringing in potassium, right, against its concentration gradient too, because you're going to be establishing in a neuron at rest because of the operation of this pump, a significantly higher concentration of potassium ions, positively charged potassium ions on the inside of the membrane. But remember, there's at the resting potential a charge difference, right? More positive outside because of all that sodium, and more negative on the inside because there's less sodium. And because the pump is unequally distributing positive charges, right? It's kicking out 3 positively charged sodium for every 2 positively charged potassium that it brings in. So that's like kicking a net 1 positive charge out every time it operates, right? And in addition, the inside of the neuron at rest, right, and the inside of the neuron just in general, has more proteins, which tend to have more negative charges associated with them because they're built of amino acids. And more of those amino acids, more of those pieces that make these proteins have a net negative charge. So here we have a system, right, at rest where, the sodium's in high concentration outside, the potassium's in high concentration inside. And you should note that when, there are the leakage channels for sodium, you see sodium going from the outside to the in. And the reason is because these forces that are operating, right, including the concentration gradient force, remember things move from high concentration to low concentration. Well, for sodium, it's an high concentration on the outside, a low concentration on the inside. So the concentration gradient force is driving it in, those leakage channels at the resting potential, right? And the electrical force, remember, opposite charges attract, is also driving the positively charged sodium towards the negatively charged interior, of the neuron, right? It's minus 65, minus 70 millivolts relative to the outside, on the inside of the cell. Now, if you look at the potassium movement, right, in a neuron at rest at minus 65, minus 70, inside versus out, right? You see the potassium actually leaving through its more numerous leakage channels from the inside to the out. And so the force that's driving it from the inside to the out has got to be the concentration gradient force. Because remember, that means things move from a high concentration to areas of lower concentration. And potassium, because of the pump, right, because it's, that dual directional transporter is utilizing ATP not only to kick the sodium out, but also to bring in high concentrations of potassium on the inside. Well, it's going to be higher inside versus immediately out, which means that the concentration gradient force will drive that potassium from the inside of the cell to the outside of the cell. Well, there's another force involved, right? The electrical force, which is a little more complicated here, right? Because it's negative on the inside, right? Because there's a charge difference that's maintained in a neuron at its resting potential, minus 65, minus 70. And potassium is a positively charged ion, so opposites attract. So the electrical force really wants to keep that potassium on the inside, right? But most of these diagrams we're going to show you will show it going out. And so that means that minus 65, minus 70, that particular charge difference, the electrical force is not strong enough to override the concentration gradient force. So these forces kind of, can be in line, with each other as they are for sodium, stored in high concentration, very positive outside versus negative inside. There's no confusion about which direction, the sodium will go. It'll go from the outside to the inside if it's given more opportunities, more open channels, right? But for potassium, it's, the forces are not aligned. So I'll just tell you, there's a complex equation actually in, the advanced class we can talk about called the Nernst Equation that you can plug all the various values of concentration and charge difference in, and it'll tell you the net flow, the direction of flow for these ions. But in a neuron at rest, at minus 65, minus 70, at that level of electrical force, the concentration gradient force for potassium is going to be stronger, so the net flow will actually be from the inside to the out. Now, that's the resting potential, right? We've got this maintenance. You've got some through the leakage channels. You got some sodium rushing in because of the concentration and electrical forces. You got some potassium going out because the concentration gradient force is winning and it's pushing out. You got the pump, moving back and forth with ATP, distributing those charges, and you maintain a charge difference that can be measured with a potential on the inside and a potential on the outside, right? That's known as the resting potential, around minus 65, minus 70 more millivolts more negative inside versus the out. But what's an action potential? Well, that's not going to be maintained the same charge difference between the inside potential and the outside, but you're going to see action between the potentials. And this is going to require a change in the permeability of the membrane to drive ions, to allow for ions to go back and forth, to allow for these forces we're describing, concentration and electrical forces to drive ions back and forth. So it's dependent upon not non-gated channels, but actually gated channels, channels that are closed at the resting potential. So they maintain that impermeability, but they open at what's called a threshold potential. So it turns out that what gates these channels, what opens them or closes them, is the charge difference itself, because these machines, these channels, right? They're called gated channels. They're actually called voltage gated channels. They're made up of proteins, right? So they're proteins. They're made up of amino acids, which have charged components sticking into the extracellular space, charged components sticking into the intracellular space, and that particular charge difference that's maintained will, deliver electrical forces, both, like charge repulsions and opposite charge, attractions on the different constituents, the different pieces of that protein that span the membrane. And at minus 65, minus 70, it'll maintain, a closed conformational state. It will not have a pore or a channel that is open. It's gated at the resting potential. But should you reduce the charge difference, and we call that reduction in the charge difference, going from minus 65, let's say, to minus 55, we call that a depolarization, right? So if we depolarize a neuron at rest, minus 65, minus 70, down to a specific, what we call a threshold potential, minus 55, well, all of a sudden, the forces have changed here. This machine called the voltage-gated sodium channel will suddenly change its conformational state. So here it is at minus 65. You hit the threshold at minus 55, and it opens a pore or hole, right? So you've got lots of these voltage-gated, sodium channels arrayed around the axon hillock, the beginning of the axon, this portion right at the start. And if you can depolarize, that axon hillock to minus 55, well, you're going to get all of these voltage-gated sodium channels to suddenly swing open, dramatically increasing the permeability of the membrane to the passage of sodium. And then, of course, that sodium is going to be driven from the outside, where it's in high concentration in a very positively charged environment, to the intracellular side, where it is at minus 55 negative, and there's very little sodium. So the concentration and electrical forces will drive it in. And as you do so, you're going to continually change that charge difference, right? If you bring all those positively charged sodium ions to the intracellular side, it's going to go minus 55, minus 45, minus 35, minus 25, minus 10. It'll actually get up to positive 20 or 30 on the inside briefly, as you got this huge amount of sodium now clustered on the inside. And this voltage-gated sodium channel is still listening to that charged environment and the change in the charge difference, the potential difference, across the membrane. And, when it hits like minus, or positive 20 or 30, it'll shut. It'll close right up into another form where it cannot be reopened until you repolarize. You go back, to the resting potential, around minus 65, minus 70, where it can reset, for another response at the threshold potential of minus 55. So this is quite a remarkable machine that is essential for the initiation of an action potential, because it's listening to the polarization, the difference in charge across that membrane. At minus 65, the resting potential, it's just like this. If you depolarize it to minus 55, it swings open like this, allowing the concentration gradient and electrical forces to drive lots and lots of sodium to the inside, where it'll continually change that charge difference, right? So now it's, positive 30, let's say, on the inside, and then it'll, close, right? And now it is absolutely not going to reopen again until you get back to minus 65 and you reset it, and then you'd have to depolarize again to minus 55 to open it up. So how do you repolarize? How do you get back? That's the second phase of this action potential, because there's another set of voltage-gated channels that are embedded in the neuron's membrane, many of them around that axon hillock, where the initiation of an action potential can take place. And these are voltage-gated potassium channels. And these will open, at a depolarized threshold, around minus 55 as well. And the potassium, remember, at minus 65, at the resting potential, we showed it leaving the cell because the concentration gradient force, remember, it's in high concentration on the inside because the pump brings it in, will be winning. At minus 55, where the electrical force has been reduced, the concentration gradient force is even stronger, right? So it'll in comparison. So the potassium will start leaving. And as you take the positively charged potassium and you take it out, well, that'll oppose that, further depolarization and reversal of polarization to positive 30. It'll start taking it back down, repolarize it, towards the resting potential and the resetting of those voltage-gated sodium channels. The other significant contributing factor during an action potential for the repolarization is the fact that, you hit threshold minus 55, right? Remember, you open those voltage-gated sodium channels. Remember, the concentration gradient and electrical forces drive all that sodium in. You got all this sodium in here. Well, that sodium is not going to stick around, right? A little bit further, down the axon, from the hillock, we're at our resting potential, which means it's minus 65 on the inside, so it's negatively charged, and there's no sodium. And, the sodium can't get out again because, remember, those channels have now closed, right? But it can move down a little ways down the membrane on the inside of the cell, where its entry will depolarize, right? You're bringing all these positively charged sodium ions in to an area that was at its resting potential of minus 65. So you're going to be reducing the difference in charge, depolarizing that next segment of membrane. And when you hit minus 55 there, well, you're going to swing open more voltage-gated sodium channels. More sodium is going to come in. You're going to open more voltage-gated potassium. More potassium is going to go out. You're going to get this depolarization, repolarization, what they call propagating down. The axon working its way down. So you get the sodium coming in, the potassium going out, sodium coming in, potassium going out, sodium going in. As it works, it propagates down from the axon hillock, until you reach, the axon terminal, where we're going to get, a change in the language of neuronal communication, from that electrical depolarization, repolarization, that wave of what we call the action between the potentials, the action potential, into, we're going to see the release of a chemical neurotransmitter, that can then influence the next neuron, across the synaptic